Howdy, everyone, and again, welcome back to my lecture series on introductory astronomy, specifically for my ASTR 103 class. I can see a typo. This is actually spring of 2022 rather than spring of 2020 or 21. Anyway, summer. Anyway, so minor correction I need to make. So now that I've stopped babbling, what are we going to actually talk about today? And what we're going to talk about in this lecture is the sun, something that is very important to the folks on the Earth because it is what provides us the energy that life thrives on. Without the sun, we wouldn't be here. If the sun were brighter or if the sun were dimmer, we would, again, chances are we wouldn't be here. The fact that we are at this distance and the sun is as bright as it is allows us to pretty much exist. So we're going to look into what is the sun. We're going to look at the sun as a star. We're going to look at how that tremendous amount of energy is produced. What does the internal structure of the sun look like? And is there what we refer to as solar weather? Spoiler alert, there is. And we're going to look at what that solar weather is. I can do this. Hey, all right. So what is the sun? Basically, the sun is a sphere of high temperature plasma. Now, plasma is a phase of matter that is more rarefied than gas, and it is entirely made up of ionized atoms and electrons. So the way that, if you look at the phases of matter, the more rarefied or the less dense, I suppose, the material becomes, the hotter temperature is responsible for that. So solids reside in fairly low temperatures. If you crank the temperature up high enough, then they become a liquid. If you continue, they become a water vapor, or they become a vapor. Or a gas, and then finally everything, regardless of what it started at, turns into some sort of plasma. This plasma of the sun is primarily composed of hydrogen and helium, with some small amounts of heavier elements in it. We know from the primordial abundance of the universe, which was hydrogen, helium in slightly different percentages. Helium was around 24%. And only a tiny bit of lithium, that the sun is not a first-generation star. In fact, it's probably a third-generation star. There were stars that formed during one epoch. They evolved. Then there were stars that formed out of the remnants of those first stars during another epoch. And then finally, the stars that are about the same age as the sun and are currently forming. The sun is about 4.5 billion years old and is expected to be around for another 4.5 billion years. When I say be around, what I'm really talking about is, the main sequence. The main sequence are stars that burn hydrogen and helium in their cores, and they are in what we call hydrostatic equilibrium, which I'll go into in a moment. The sun will continue to be on the main sequence for another 5 billion years, and then it will very quickly evolve off the main sequence and very quickly evolve basically to its end state, which is a white dwarf. I will be talking about white dwarfs in lecture 16, if memory serves. So, what can we say about the energy generation of energy from the sun? This is tied to how we know that the sun is as old as it is. There are essentially two other hypotheses. There were two other hypotheses that were put forth in order to explain why the sun is hot or why the sun produces energy. One of which was a chemical reaction, an exothermic chemical reaction, and the other was conversion of gravitational potential energy into kinetic energy and thus heat. The problem with the problem with the previous two was lifespan. We know the mass of the sun, so if you look at chemical reactions, we also know that it is, again, the composition is primarily hydrogen helium. If you can make that burn in a chemical reaction, then the sun would have burnt out after a few tens of thousands of years. It would have burned, the fuel would have burned very quickly, and so the sun could not possibly be around, because we know from Earth-based observations that the Earth is billions of years old, so it didn't quite fit. And then the argument for conversion of gravitational energy into kinetic energy, that produced a much longer time frame of a few 100,000 years, but again, far outside the ballpark in terms of what we know about the Earth's age. The only mechanism that we know of that can produce this amount of energy over such a long time frame is nuclear fusion. And so I'm going to be talking about two different types of nuclear energy, fusion and fission, just to illustrate the differences between the two. But I want to emphasize that nuclear fusion is what is going on in the core of the sun, and it is what is generating the 10 to the 26 joules of energy per second. So, and that amount of energy is what supplies the energy for life on the Earth, nearly 100 million miles away, or around 149 million kilometers away. For those of you who are lucky enough not to use imperial units. And so like I said, there is a tremendous amount of power. It is generated through nuclear fusion as opposed to nuclear fission. The basic or short answer as to why we don't use nuclear fusion on the Earth is that we cannot sustain the environment needed for nuclear fusion over any significant time frame. We have successfully created fusion. We have successfully fused hydrogen. However, if memory serves, we were only able to obtain it for a few seconds, because, as we'll discuss, the circumstances or the environment in which you need the environment which is conducive for nuclear fusion to happen, you need exceedingly high temperatures, you need exceedingly high pressures and densities. So when we talk about nuclear fusion or nuclear power on the Earth, what we are describing is nuclear fission. So before we get into that, let's talk about hydrostatic equilibrium. Hydrostatic equilibrium is a fancy way of saying that the sun is stable, or at least stable to first order. It does pulsate a little bit on a order of about 5 minutes, but overall, if you were just to sit back and look at it from any sort of distance, you wouldn't be able to tell that the sun is vibrating in any way. And the reason for that is because it is stable. There are two fundamental pressures which are competing against each other. The first, obviously, is gravity. Gravity is attempting to bring the sun, or collapse the sun down to a singularity, as it were, or very, very small object. And then you have radiation pressure. Radiation pressure is energy, essentially the pressure of the energy which is generated from the core of the sun. Light exudes a small amount or exudes pressure. The reason why we don't experience it in our terrestrial lives is because the amount of pressure exerted on us is very, very small, because of the amount of energy that these lights put out, and the lack of photons, or the lower the number of photons which are actually hitting us. But in the sun, you're talking about extremely high temperatures, and a lot of these photons are streaming out of the core. So the sun is in what we, like I said, what we refer to as hydrostatic equilibrium. What that means is that gravity, the inward pressure of gravity, is essentially equal to the outward pressure of radiation pressure. Now, when we look at nuclear physics, we have to sort of understand what are the things, technical term, what are the stuff that is involved. And you probably already know that this involves atomic nuclei. And so with fission, you're talking about very large nuclei like uranium. With nuclear fusion, you were talking about smaller ones like hydrogen, helium, carbon, so forth and so on. And so nucleus is composed of two objects. You have protons and neutrons. Protons are positively charged particles. Neutrons are neutrally charged particles. And these are referred to as nucleons. Now, you can have different isotopes, and isotopes mean isotopes is a word meaning that you have an atom of a particular element, but it has more neutrons in it than the standard model, as it were. So, one of the key factors in producing this energy is locked up in what we refer to as the binding energy. Now, there are four fundamental forces. There is gravity, there is electrostatic, there is weak, and then there is strong. Electrostatic tells us that if you have two charged particles that have the same charge, you have this repulsion. The two objects do not want to don't want to have anything to do with each other. It's like putting a north end of a magnet next to a north end of a magnet. It's gonna be real hard to get those two to actually see eye to eye. But then you have the strong nuclear force, which is, as you might expect, because astronomers and physicists are not the most original people in the world, it is a strong force. In fact, it is the strongest of the fundamental forces, and it easily can overcome the electrostatic repulsion. But that takes a certain amount of energy to actually hold these things together, and this is what we refer to as the binding energy. Now, if you can release that binding energy through some means, if you can break apart these protons and neutrons into different components, then you can release that binding energy, and you can get energy. You can get energy out of it either through fusion or fission. Now, here are the binding energies as a function of elements, and as you can see, that the binding energy, if you start with hydrogen and move up, we find that the binding energies of hydrogen, of different isotopes of hydrogen, are fairly low. Because the amount of number of protons there is small. It doesn't take a huge amount of energy to break that apart. Then you got helium, lithium, and the amount of energy, as these elements get larger, the amount of energy is needed to break these things apart increases until you get to iron. And then, after iron, as you get to larger elements, even larger elements, the binding energy actually drops until you get down to about uranium, which is one of the reasons why uranium is ideal, as it were, for nuclear weapons, as Chekhov might say. Now, iron is special because if you can look at the top of this graph, it has the highest binding energy. But in fact, its binding energy is so large that if you were to fuse iron together, you get less energy out than you put into it. So it doesn't happen naturally. Same goes for fission. If you split a iron atom, you get less energy out than it takes to split the thing. So again, hence why it doesn't happen naturally. It's actually impossible to do. So here is just basically saying that iron is one of the most stable elements in existence. It has the largest binding energy per nucleon of any element in the universe. And what we're going to find later on when we talk about the end stages of very high mass stars, iron essentially is it. It is the final elemental core of very high mass stars. It cannot fuse into something else. So as I said, there is a difference between fusion and fission. Fusion is the combining of smaller nuclei into larger ones, and fission is the splitting of larger nuclei into smaller ones, very simply put. And both of them release energy. Both of them release energy due to these interactions. And this release of energy, we can thank Einstein for cluing us in as to why this happens through his famous equation E equals mc squared. Now, I love, and I've probably mentioned this before, I love the fact that some of the most powerful equations in the universe, or in physics, are very, very simple, at least to first order. You have m equals ma, you have E equals mc squared. These are very powerful statements, expressed very, very simply using mathematics. Now, one of the consequences of this equation is that energy and mass are effectively the same thing. They are one can transform into the other. Energy can become mass, mass can become energy via this relationship. And so, from a fusion standpoint, well, really in either standpoint, what happens is that the total mass of the system drops very slightly, and that mass is released as the energy. And we'll discuss with fusion, for each individual fusion reaction, that amount of energy or that mass loss is very, very small. And so, with both fusion and fission, one of the points that I want to emphasize is that the amount of energy that is released via a single reaction, via a single atom or couple or pair of atoms or colliding atoms, is very, very small. With fission, a single uranium nucleus is only about 10 to the negative 11th joules when it gets split. In comparison, a AA battery holds about 10 to the 4th joules. So splitting the uranium nucleus, a single uranium nucleus, is orders of magnitude has orders of magnitude less energy than a AA battery. Now, the reason why you get such massive amounts of power from nuclear reactions is because there is a tremendous number of uranium nuclei that is being reacted, or I should say, for an atomic weapon. The reason why you get such a large bang is because there is a considerable amount of uranium nuclei, each contributing this small amount of energy, which adds up very quickly. So when we look at fusion, we look at uranium-235, and this is the material that was in Little Boy, the nuclear weapon that dropped. I think that was on Hiroshima. Could have been Nagasaki. I think Little Boy preceded Fat Man. I could have that backwards. Anyway, uranium, when it splits, it creates energy that's powerful enough that it first comes out as X-rays. Remember from our discussion of energy, X-rays are shorter wavelengths, and therefore they carry more energy than visible light, for example. And then you get a number of byproducts, notably of which you get cesium and rubidium. Now, one of the problems with fission reactors is that the material that you get out of it is radioactive, and then we really can't do anything with it. Basically, it's waste. It's radioactive waste. So that's the main drawback for fission reactors as a mainstay power source. Is ultimately trying to figure out what to do with that. With fusion, fusion is essentially clean. You do not have a radioactive element afterward, because helium is pretty stable. So in order to get uranium, uranium is an isotope, and it's not the most common form of uranium. So you need to enrich it in some way. And so by the way that you do that is you bombard it with neutrons, and you get neutrons from a different element and from a different source, and basically those neutrons decay off that particular element and then slam into uranium, and wham bam, thank you ma'am, you have uranium-235. Again, this chain reaction can be controlled for the most part. People at Chernobyl found differently, but you can control it in nuclear power plants, and then it's not controlled in nuclear weapons. Now let's get to fusion. Fusion is much nicer than fission, in my opinion. And you have fusion occurs in the sun through what is referred to as the proton-proton chain. I refuse to call it by its acronym. For the same reason I refuse to call Uranus by its proper name. My inner 5-year-old just can't seem to handle it. Now you have step one. Step one is you take two pairs of hydrogen atoms and you slam them together at very high speeds, and you produce a certain amount of energy and a positron, a particle of antimatter. That gets quickly destroyed and actually creates energy in and upon itself when it slams into an electron, its matter counterpart. They annihilate each other. And then you also get a gamma ray out of that. The end product is a deuterium atom, which is an isotope of hydrogen. And so in step two, you start off with two deuterium atoms and two hydrogen atoms. You slam those together, and you get gamma rays out of that. You get energy out of that, and then you take and that produces what we refer to as helium-3, which is a particular isotope of helium. Those smash into each other and create a helium-4 nuclei, or what we refer to as an alpha particle, and two protons get thrown out. Now, a proton is simply a hydrogen nuclei, so you can say that two hydrogen atoms get popped out. And then that process cycles through and repeats itself. And again, each individual reaction is not very powerful. It's only because you have trillions of these reactions happening at any given second that you add up or obtain the amount of energy in the core of the sun. But as I said before, this process requires very high temperatures, 10 billion Kelvin, and very high densities and very high pressures. So these two slides really just reiterate what I've just said about the proton-proton chain and how it works. Here is the inputs and outputs. The inputs are four hydrogen nuclei, and the net outputs are one helium-4 nucleus, two positrons, two neutron stars, and two gamma rays, and a partridge in a pear tree. That partridge doesn't last very long. So this is what I was talking about in terms of how little energy you get out of it. The total amount of mass that converts into energy from this entire process. So if you add up the total amount of mass from four hydrogen nuclei, and then you look at the amount of mass of a alpha particle and two hydrogen nuclei, the total difference is 0.7% of the total mass of hydrogen. And so of the initial hydrogen. So the amount of energy is from E equals mc squared. You have 0.007 times the mass of hydrogen times c squared. And I will let you in on a little secret. That is a very small number because the mass of hydrogen is very small. So now that we know how the energy is actually produced, how do we actually get it out of there? How does the energy from the core of the sun actually manage to make it out and then get to us? Well, before we can really talk about that, let's talk about the layers of the sun. So we have ultimately 4 internal structures. Like, in a vague way, you can think of this as core, mantle, and crust, if you want to equate this to a terrestrial planet. So you have a core surrounded by a radiative zone out to about 70% of the volume of the sun, and then the remaining amount of volume is the convective zone, and all of that is surrounded by what we refer to as the photosphere. The photosphere is referred to as such because it is where the light, all of the light of the sun, leaves the sun and moves out into space. Now, the sun's quote-unquote atmosphere contains of 2 structures, the chromosphere and the corona. If we look at the interior, what we see in terms of density is that you have a fairly linear, is that log? Fairly, I think that's log, an exponential decline in density from the core to the convective zone. It's a nice continuous drop. When you get into the convective zone and near the end of the edges of the sun, it drops off precipitously once it gets to the photosphere. So the core of the sun is about 160 times denser than water. In the radiative zone, it drops off to about 1/5 the density of water. So you can see the sun is highly concentrated in terms of mass. There is a lot more mass. The density is far higher in the core than it is anywhere else, and that is what contributes to the environment necessary for nuclear fusion to exist. And you get something rather similar in terms of temperature. You get a nice, comparatively slow drop in temperature with relation to distance, and then it drops precipitously with the convective zone. I think it cut off. The orange is radiative zone, red is convective zone, and then you get to the photosphere. So the temperature drops off in the sun from 15 million Kelvin in the core to roughly 5,800 Kelvin, the photosphere. So again, a rather precipitous drop, most of which is in the convective zone. This is simply just reiterating what the... Oh, I'm sorry. This is not reiterating. This is talking about the sun's atmosphere. Reading is fundamental, kids. Stay in school. So we have 2 structures. We have the chromosphere and the corona. Now, incidentally, if you look at the density profile continues to drop, and actually it drops to a very rarefied gas, or very rarefied plasma, as it moves out. Temperature, on the other hand, inverts. Temperature, as it moves out, it gets hotter in the chromosphere to tens of thousands of Kelvin, all the way out to the corona, which is higher up, and it's 1 million Kelvin. But you might be curious why the satellite we've recently sent to the sun didn't melt when it entered the corona. And that's because while that is really, really hot, the way that we experience heat is through interactions with the medium that we're in, i.e. the air molecules slam into us, and the conversion of the motion of those atoms or those molecules slamming into us turns into heat and warms our bodies. And so the air, while it's not overly dense, is dense enough that we experience a proper amount of heat to live. The corona is way, way less dense. The coronal density is around 10 orders of magnitude lower than the density of the photosphere, and the density of the photosphere is orders of magnitude lower than the air around you. So we're talking about exceedingly rarefied gas. So So each individual, if you get hit by a particular particle, then you get a tremendous amount of energy from that particle because it is traveling at a very high rate of speed due to the temperature. But you're not going to be hit by very many, and so you're not going to experience the same thing as if it were 1 million Kelvin at room or in room pressure or sea level, for example. So it just means really at the end of the day, what it really means is that the coronal gas is just moving really, really fast, and the reason for that is tied to magnetic fields, which I'm going to touch upon, but in this case, that's beyond the scope of these lectures. That tends to get fairly complicated. So, what about the interior of the sun? And so, what we have is the differentiation between the radiative zone and the convective zone is determined by essentially energy transport. So we have gamma rays being generated through the nuclear fusion, and we also have neutrinos being generated via the proton-proton chain. Neutrinos are exceedingly weakly interacting particles that have a very, very small mass, to the point that we have not been able to precisely measure the mass. We have upper limits as to what the mass could be, but we have not, our instrumentation is not precise enough to actually measure what that mass is. We know it has to have mass based on other experiments that have been run, but we don't know what that is. Those neutrinos, because they interact very weakly with anything, easily escape the sun and then stream out into the multiverse. And currently, there are tens, if not hundreds of thousands of neutrinos streaming through you right now. So because they're weakly interacting, even though they have a tremendous amount of energy because they're moving close to the speed of light, they don't hurt. They aren't going to cause any cancer because, again, they don't interact with much. Gamma rays, on the other hand, interact pretty easily with things, and they will bump into stuff. And during each interaction, the photon, the original photon generated through nuclear fusion, is going to lose a little bit of energy. It's going to basically get thrown into a different direction. And we do this, and it does this through what we refer to as a random walk process. Now, the way I like to think about this is a drunk trying to get to the bathroom. Now, once they realize they have to go to the bathroom, they're going to plinko their way through the bar until they actually get to the bathroom. So the photons are essentially that drunk person. They are generated in the core and they stream outward. They will slam into something. They will slam into either another photon or an electron or a nucleus an ion, and they will get redirected. That's really not precisely true. When they do so, there's going to be an exchange of energy. And so the energy gets absorbed and it's going to be re-emitted. Sometimes it might get scattered. But that energy is going to be lower than the initial energy. And so gamma rays will eventually start shifting down to X-rays, ultraviolet rays, and lower, and even lower. It takes a very, very long time for photons to escape the radiative zone. Over 100,000 years in order to get out, to basically this random walk. It's a very crowded bar. It takes a really long time for it to go out. And you might be asking, why does it go out? Why does it move outward? Well, if it's truly random, it should be going anywhere. But the reason for this is because of that density drop-off. The likelihood of smacking into something moving outward is less than the likelihood of moving something inwards. And so, 100,000 years later, that original bit of energy is going to hit the convective zone. And the convective zone is, because of the internal, simply put, because of the internal chemistry of the plasma, or at that point, It is more efficient to carry energy via convection as opposed to this random radiative process. And what we have is that neutral atoms, it's cool enough that neutral atoms can exist, and they absorb photons, very much like we talked about before through electron orbit transitions. And that heats up basically heats up a what's the word I'm looking for? Packet of energy, or packet of plasma, and that causes that packet of plasma to rise. The hotter something is, the less dense it is, and it's going to rise. Is that right? Well, the hotter something is, the more it wants to move outward. Less dense. Yes, less dense is going to cause it to move outward. Until it gets to the photosphere, it's going to release that energy into space through radiation, actually, and then that piece of plasma is going to drop down, and that process is going to repeat itself over and over again. Fairly similar to boiling. Now, this diagram, as many diagrams of this sort, is a simplification. Convective motion is much more chaotic than what we see here, but you get the idea from this. It is a much faster way of transport in the fact that, depending on the star, you can have the time frame is on the order of days to get energy from 0.7, the radius of the sun, all the way out to the photosphere. And see here, what we can see is the convective action. Again, the hot gas rises in the center, it flows up, it releases its energy out into space, and then that cooler gas or cooler plasma will fall back down into the inner regions of the zone, pick up more energy again, and then move off in that way. And the reason why we know this, we have some indication of this based on visible observations of something known as granulation, which I'll touch on later on. We can literally, if you watch in real time, you can literally see the convective action on the surface. Now, in order to really be able to describe it, in order to really be able to say that what we're seeing is upward motion as opposed to downward motion, we use something which we refer to as helioseismology. The sun is so large with respect to other stars that we can isolate, or we have the angular resolution to isolate small packets of the sun. So we're not looking at the entire sun, we're looking at small regions. And we can use the Doppler effect to determine whether or not that region is coming at us, or getting blue shifted, or falling away from us and red shifted. Now, again, with this diagram, it's a simplification, but it gives you the basic idea. The blue is the brighter parts of the convective cell. That is where the energy is rising up from underneath, and then it flows out on either side and recedes away from us, hence the redder areas. And it is through these types of observations that we can nail down the models of the sun. You might be asking yourself, how do we know that there's a convective zone? How do we know that there's a radiative zone and a core, and so forth? It's because we have observational parameters. We know the mass, we know the radius. We can see that there is this helioseismology. We have these, what we refer to as boundary conditions that essentially limit what the model can do. And so we generate a model based on some physical process, in this case nuclear fusion, and we tweak that model until the resulting energy that we get out of it and its behavior is what we see. So let's talk about activity on the sun and beyond. And this is my favorite part. It is a word of this discussion. Particularly sunspots. I am very particular. I am very partial to spots. During my dissertation, I actually looked at star spots, spots on the surface of other stars, but sunspots work too. So here's a picture of this granulation that I was talking about. You have bright regions in the center, and then that gas cools off and falls away. Just to remind you of the Stefan-Boltzmann law, what that says is that the luminosity or brightness of something is related to the temperature. And so those bright regions are of a higher temperature than those dimmer regions. And I'd like you to keep that in mind when we talk about sunspots. Well, right now. Sunspots appear as dark spots. Galileo was able to see this through a projection of the sun, and actually he was the first one to determine that the sunspots exist, and that through them he was the first to observe sunspots, and through his observation of sunspots he was able to determine that the sun rotates. But it was only until later, when we had higher resolution, that we're able to see that sunspots have definitive structure, basically two different structures. You have the umbra and the penumbra. Now, the penumbra looks dark, but it is by no means cold. It is about 2,000 Kelvin cooler than the photosphere. So if you picked the plasma out of the sun that's umbra and put it in the night sky, it would glow like a star. The penumbra is only a few hundred Kelvin cooler than the photosphere, hence why it appears an intermediate. It's certainly not black, and it's certainly not as bright as the surrounding area. And these sunspots are about the size of the Earth. They can change in size fairly dramatically. There's a large range in the sizes, but on order, sunspots are about the size of the Earth. And hopefully when you were looking at the sunspots, one of the things that you first noticed was, if you look at the penumbral region, you can sort of, if you squint, you can see this filamentary structure within the penumbra, which is reminiscent of, or basically a product of what, or gives a hint of what's causing it. Imagine iron filings against a bar magnet. You get a similar sort of pattern. And that leads us to understand, particularly through other observations, the Zeeman effect is one of them, that the sunspots are magnetic in origin. It is because of localized magnetic fields, or localized strong magnetic fields, that these spots exist. What is happening is that the strength of the magnetic field actually creates another pressure which impedes the upward motion beneath it. And so the photosphere does not get nearly as much energy from beneath it than it would ordinarily if the magnetic field was behaving itself. And one of the other reasons why we know that this is we highly suspect, we have good confidence that sunspots are magnetic in origin, is that they have different polarities. Depending on the state of the sun, we'll talk about the sun cycle in a moment. If you look at the magnetic polarity of one spot in relation to its pair, one spot in the northern hemisphere could be a north polarity, the other spot is south polarity, and that's flipped when you go to the below the equator, the solar equator. And because they are magnetic in origin, sunspots typically appear in pairs. They can also appear in groups, as you can see in the lower end. Lower in the southern hemisphere, that large blob is actually composed of many different sunspots. But if they're isolated, they occur in pairs. Now, we have an exceedingly long record of sunspots. People have been looking at the sun for a very, very long time. One of the reasons for this is because in the early 1900s on Mount Wilson Observatory, they built a 60-foot long solar telescope. The focal length of it was 60 feet. That was then surpassed by 150 feet. And that has provided us almost a continual record, besides, cloudy days, continual record of the spots on the sun. And what we notice from looking at that record is that there's some kind of periodicity. It seems to be cyclic. What we have is, and we refer to this as the butterfly diagram, because obviously they kind of look like butterflies. What we find is at the beginning of the cycle, you have a smallish number of sunspots that exist, that form at fairly high latitudes, or they form around the mid-latitudes, around 30 degrees plus north and south. And then as the cycle moves along, you get more sunspots forming, but they form at lower altitudes. They form at lower latitudes, north and south, until finally there are no sunspots whatsoever for a few months to a year, and then we see spots occur at those 30-degree latitudes again. Incidentally, what we also see is that the polarity of the sunspots flips. So if you had a north-south, if we're looking at the northern hemisphere, if you had a north-south polarity of spots in the first cycle, in the second one, you'd have south-north as you move forward. What we also find is that this, as you might be able to see from these butterflies, all of these butterflies are not the same size. So we can compute, or we can measure the number of sunspots. It's actually kind of a kludgy measure, but it's close enough for government work. And we can we can count the number of sunspots that are actually on the surface. And what we see is, again, we see this periodicity of around 11 years, where the sunspots go to a maximum and then drop off. But there are two noticeable things here. One, solar activity. The amount of sunspots, the maximum number of sunspots, is not constant. Sometimes the maximum number is fairly low. Sometimes the maximum number is relatively very high. What that indicates to us is that the sunspots are a proxy for the strength of the magnetic fields, or the strength of the solar dynamo. So the sun is more active, more magnetically active, when you have more sunspots on its surface. The sun is less magnetically active when you have no sunspots, or fewer sunspots. And what we also find is, and this is counterintuitive, the more sunspots you have, the higher activity of the sun, the more sunspots you have, the brighter the sun is, or the more energy is being produced in the sun, which leads me to the Maunder minimum. The Maunder minimum happened around, as you can see, from around 1650 to 1700, and it corresponds to, or it aligns fairly well with the Little Ice Age in the Northern Hemisphere. During this time, the Thames in London would routinely freeze over, and then they would set up basically a fair on the Thames, and you can enjoy that and what have you. That obviously doesn't happen today. The Thames does not freeze over during winter. It is suspected that the Maunder minimum had some relationship to why the Little Ice Age occurred, but it was not the primary driver of the Little Ice Age. It certainly didn't help much, because again, the sun was cooler, and so the overall radiation what we were getting from the sun was lower, and so things could get colder. So why do we have these magnetic fields at all? Or why do we have these sunspots at all? This lecture brought to you by Coca-Cola. It is because that the sun is not what we refer to as a solid body rotator. The Earth is a solid body rotator. The length of a day at the equator is the same as the length of the day at the poles, 24 hours. That is not true for the sun. It is what we refer to as a differential rotator. While the core is solid body, a core rotates around 27 days, the synodic period. If you were to measure the rotation from the Earth, it would be 27 days. But the envelope, the convective envelope, is not solid body rotating. atmosphere. So the gas around the equator moves around 26 days, and then as you get to higher and higher latitudes, it gets up to 34 days. So it moves faster at the equator, moves slower at the poles. When astronomers refer to the overall rotation speed or rotational period of the sun, we canonically give you what is known as the Carrington period, which is roughly around 27 days. It's somewhat of an average of the different periods that we see, or the different movements that we see. Now, why is this important? Why is this important? It's because magnetic fields get trapped in that plasma. And so, at the beginning of a cycle, you can think of the sun as a bar magnet. Again, to very first order. It's far more complicated than that. But to very first order, you can think of the sun as a bar magnet. You have a north pole, you have a south pole. But as time progresses, and that differential rotation brings the equatorial material around faster, the magnetic fields that are trapped in that plasma bend or get twisted. And so you can see over time you get these magnetic fields become twistier and twistier, technical term. And on top of that, you have localized disturbances. You have localized kinks within these magnetic fields, and that is what generates sunspots. It's what generates solar prominences, flares, and potentially coronal mass ejections. Ultimately, this is not as you might say, a tenable or a long-term. This is going to break. The sun cannot sustain this. The magnetic fields cannot be twisted ad infinitum. At some point, the magnetic fields are going to reorganize themselves back to a bar magnet polarity. And when it does so, it's going to have a flipped polarity. If you remember when I was talking about sunspots, if you're looking at the northern hemisphere, at one part of the cycle, it's north and south. The first spot is north, second spot is south, and then it flips. That is because the overall polarity of the sun also flips. And then it goes through this twisty action, and then it comes back to north at the top, south at the bottom. And so the overall solar cycle is actually 22 years. It's double that 11-year period, or 11-year cycle we see with sunspots. Now, what about solar prominences? Solar prominences occur in the chromosphere. And ultimately what you have is these magnetic fields which are in the plasma, and for reasons which I will not get into, which are beyond the scope of this class, the radiation ultimately pushes these magnetic fields out from the surface, and you get these arcs. And so when you have these magnetic fields, what that does is that if you have charged particles in the corona, which you do because of the higher temperatures, those charged particles are going to essentially condense onto those magnetic fields, and you get a denser gas, which is brighter. Now, this is a YouTube, or a clip from a YouTube video that I've made, and there's the link to it. Prominences last a few hours to a few days. This observation was taken with NASA's Solar Dynamic Observatory, which is an orbital satellite, which is continually taking observations of the sun. If I had to guess, this was taken in the H-alpha filter, so we're looking at primarily hydrogen gas emission. But you can see the gas is raining down onto the surface. It condenses at the top of the arc, and that gas rains down onto the bottom. It's tracing those magnetic field lines. It is, while I love spots, solar prominences, I could watch them for days, because that's usually how long they last, a few hours to a few days. Why do I apparently have 2 slides of that. Okay. So what about solar flares? Well, you may have heard of solar flares. Solar flares are exceedingly energetic phenomenon that occur on the sun, and they will last maybe a few hours to a few days. Now, this happens because there is a lot of energy trapped up in these magnetic fields, and these fields will also get twistified in a localized environment, not just globally, but also in a localized environment. And when it does so, these magnetic fields can ultimately snap and then reorient themselves, which we refer to as magnetic reconnection. And that process releases a large amount of radiation. And that flare flies out essentially radially from the sun. Now, if we are unfortunate enough that a flare is aimed right at us, that can drastically affect or be very dangerous to folks in orbit. So the ISS is very cognizant of what the sun is doing at any particular given time. They're not predictable, but it's certainly very monitored. The energy that is released is in light, and so it travels. It takes about 8 minutes for the energy from a flare to get to the Earth. Here's another video, and I won't talk as much. Oh, the M6.7. Think of that as like strength, like earthquakes, the Richter scale. And before I shut up, these images are taken in various ultraviolet wavelengths. Hence why they're different colors. Solar flares typically, so prominences, the 2 arcs that we see in the prominences, the bases of them, generally speaking, are sunspots, and then a prominence could in fact be a progenitor or a sign that a flare is going to pop off in that region. So a lot of these, because these are all magnetic in origin, there's a lot of overlap as to the locations for each individual things. Now, there is another explosive event, which we refer to as a coronal mass ejection. Here we have with flares, it's a large release of energy. Here you have a large amount of matter being blown off the surface, streaming through streaming through space, and this material is traveling because it's matter and not all light. It's traveling much slower, so it takes about 3 to 5 days to actually reach the Earth. Now, these, again, depending on the orientation of them, if they pop off and actually pop off in the direction of the Earth, this can have serious implications for life on the Earth. We know of 2 times that a coronal mass ejection hit the Earth. One was during the 1800s, and it caused telegraph wires. The material, once it hit the Earth, it interacted with telephone or telegraph wires and caused them to burn, catch fire to some of these telegraph stations. In 1989, we got hit by a glancing blow from a coronal mass ejection, and that took out the power of the American Northeast and Quebec, and took it out for many, many hours. And so with their more modern age, now that we have a plethora of satellites up there, we have astronauts and cosmonauts up there, if we get hit by a coronal mass ejection again, it's going to, even a glancing blow, it's going to have massive implications to our satellite communications and our space exploration or space research up there. And these are not, again, predictable. And there's really nothing we can do about it. So, sleep tight. Here's another video which explains or shows the difference between coronal mass ejections and flares. Primarily how much larger coronal mass ejections are in respect to the size of flares. This is also a YouTube video, which I think I've included the, where's my cursor? I included the URL. These are taken by a couple of different satellites, primarily the ASTR, which you can see there. And I believe, for some reason, that's twice. Oh, I will end, actually, that's not quite the end. I will very quickly talk about the solar wind and the solar heliosphere. Now, again, these are related to magnetic fields. Because the corona is very hot, at least from a kinetic standpoint, these particles are moving at very high rates of speed. And they are moving fast enough that they escape the sun, and we have this almost this radial wind of highly charged particles which stream out into space. Now, some of this wind gets blocked by the corona itself. It interacts and with these particles slam into other particles or scatter and essentially get held up, as it were. But as with all things, it's not homogeneous. Because of the magnetic fields and because of the complicated structure of magnetic fields, you can get what we refer to as coronal holes. The corona will be pushed out and rarefied enough in these holes that the particles are able to escape along magnetic field lines. And so you have a higher concentration of solar winds in that regard. Now, very much like the sun, or the Earth rather, the Earth has a force field, which we refer to as the magnetosphere. The sun also has a force field, where we have that is essentially the boundary between the solar system and the space, outward space, or interstellar space. That's the word. And so we get the heliosphere is created because you have these these very fast moving particles moving outward, and then they slam into what we refer to as the interstellar medium, the gas which is just naturally just kind of hanging out in space. And as the sun plows through the the galaxy, around 220 kilometers per second around the center of the Milky Way galaxy, it's going to create a bow shock. These very fast particles are going to slam into the very slow particles of the interstellar medium and create what we refer to as a shock wave. And this is, for the sun, we refer to this shock wave as the heliopause. And so, what's the word I'm looking for? And so, like I said, the heliosphere is one way of differentiating between, or having a physical differentiation between the sun and the rest of interstellar space. And we actually have at least one interstellar craft at this point. Voyager 1, which was launched in 1976, has actually moved through the heliopause and is now in interstellar space. So we have branched out. We have satellites beyond the scope of our solar system. And with that, I am going to end, and lecture 14, I'm going to be talking about the interstellar medium, or the stuff between stars. I'm going to be talking about how the interstellar medium, the structures of the interstellar medium, how that affects observations, and more importantly, what are the consequences of interstellar medium with regards to stellar formation. All right, I hope you enjoyed the lecture, found it to be informative, and I look forward to seeing you next time. All right, peace out.